And we're covering this book, and it is a sub-part of the chapter for Hall forms. And Hall proportions, we already see some of them. The length depth ratio, and that is more related with the structural design. Because ship is usually long and thin, similar to the shape of airplane body. The structural part in the middle, bending, is most critical failure mode. So depth and length ratio, or slender beam, something like that, is good or important for structural design. And length beam ratio, it is related with maneuverability. You have a nice discussion on form proportions on maneuverability or in previous discussion. So maneuverability has two options, as Sunguli pointed out, that there is a turning ability, and also another one is a course keeping ability. That is different options for. So one ship with good turning capability is not good for course keeping capability. And the other one is length depth ratio. And if length depth ratio is depth is shallow, then that can be a bow slamming damage during high wave. Slamming means ship bottom is hit by, damaged by water slamming, water contact, high-speed contact. And then beam depth ratio, it is related with stability and also wave-making characteristics. And CB divided by length spread ratio is a complicated compound ratio proportion. It is related to the maneuverability again. You see that, and this is, you see that three different hull lines drawings or designs, thinner or flatter or fat ships. So CV may be different for each type. And then length breadth ratio or length beam ratio. At the top left box shows you tanker and bulk carrier and speed range of 17 to 15. And length beam ratio is about between 4 and 9. And the container ship has more speed, like 23 or 19 between knots. And then the vertical axis means the resistance in percentage. So length breadth ratio, if you have a higher length breadth ratio, you may expect a lower resistance. So ship is more slender. Okay? And then final box shows a cruise ship or ferry ship. Speed is similar to container ships, but a little bit higher. And length breadth ratio and resistance shows a similar trend. Right. Here you can see the fullness and speed relationship. So form coefficient estimation and CB is a block coefficient, can be estimated or by using this kind of equation. And this equation shows you something like this curve, like this one. So usually the ship designers collect many good ship lines and proportions. And then each point on this graph is single ship. So here you may see that about 100 ship is collected and show you spectrum of this distribution. And a horizontal axis is block coefficient, and the vertical axis is Froude number. Froude number means the speed and length ratio. And at the box, you see that ship type, bulk carrier, tanker, container ship, ferry boat, and block coefficient is decreasing as ship types is moving, and ship speed is also increasing as ferry and container ship is high speed and bulk carrier is low speed. So here, once again, the equation to arrive at a block coefficient, the curve shows that based on Froude number comes from speed. Okay? So based on speed, you can estimate the block coefficient. So if you have a high block coefficient, the speed length ratio is low, so speed is low. But with a slender body or low CV, you may expect a higher speed. And then the whole form lines drawing, you can see that this is an old type of drawing room, because we need to have a template to build a ship. So ship skin is made of a curved surface, so that it is not easy to make that curved steel plate. The thick curved, something like a 2 centimeter thickness of steel plate should be bended to make a curved shape of the ship. So that each design section, they make a full size template to check whether the ship curves are correctly built. So this room is made of a big floor that full size ship sections can be made using a wood plate like this one. But nowadays, this room is not used anymore, because we can use computer drawings instead. Also, numerical control machines are used to check whether the ship surface is correctly made. So the drawing or lines, they draw, because the curved three-dimensional surface is not easy, and also the steel plate is made of a flat plate. Also the flat paper, and so that we need to have a full size, big size floor for model loft. Something like a soccer ball and tennis ball, how can you make that ball out of flat leather skins or gum plate? So out of a flat sheet, you need to make a curved shape. So that is the problem of making shapes similar. So series of two-dimensional contours are used to show that parallel crosscuts of ship, and also car body, and also airplanes too. So cartographers, they use maps using contour curves or with constant elevations. So something like this one. Okay. So on the map, you have many curves, but each curve has a contour of same height. Okay. And that height can be shown here as a flat drawing, but also you can use a three-dimensional view of landmark. So similarly, the ship is drawn by using lines drawing, gives you the body plan at the front, red part, body plan. This is a front view of the ship. And then side view is usually called the shear plan. And top view gives you a half breadth plan. So only half portion of the drawing lines are drawn in the flat space. Also, body plan shows half breadth curves of front part and after part. So it is very similar to this map drawing contours. Right, so this is the main drawing for lines drawing. One of the most important drawings, 3 important drawings, body plan. Shows you sectional curves of each plane. And here you see that there is numbers. Each number shows station numbers. You start from AP, and then number 1, 2, 3, 4, 5, 6, 10, and 11, 12, and to 20. 20 means FP. Here again, in the side view, you see that AP and then FP, and between them, it is a number of stations, 1, 2, 3, 4, 5, 6, 7, 10, and up to 20. Now, we come back to the length scale of length of overall, and also length between perpendicular. Right? And you should remember that length between perpendicular is the important for shipbuilding and designers. So that you need to divide this LBP into 20 portions of stations between AP and FP. We call this is LBP, length between perpendicular. And then division or stations is made by dividing this LBP into 20 parts. And each one has sectional dimensions like this one. And also here is the water plane lines. That is a top view. And water plane is starting from number 2 bottom tangent line, number 2, number 4, 6, 8, and 10. So this is a 2 water line, 4 water line, should be meter, 2 meter water line, 4 meter water line, 6 meter water line, something like that. And then here is the upper deck. It should be the main deck. So up to there, we call this is a depth of the ship. All right, so this is a typical lines drawing of the ship. So this drawing defines the curved surface of the outer skin of the ship. Right, here is the one video, so you can see how the design is done by this one. Okay. This.
We can use even paper drawings if necessary. Based on initial information, hull surface can be created quickly, and with high quality. Decks, appended parts, and all necessary surfaces can be also created. Initial stability data, such as displacement and center of buoyancy, can be controlled. Hull shape optimization. Modern methods of computer fluids dynamic lets us to make ship resistance predictions. Results of the CFD calculations can be visualized together with hull lines. Waves pattern, pressure distribution around hull, streamlines show us area of the hull surface we can improve. After several CFD runs, hydrodynamic quality will be optimized. Hull shape output files and documentation. Output documentation can be presented in several different documents. It can be classic lines drawing, lines and sections by customer request, offset table. Faired hull surface can be exactly transferred to most of known CAD systems. Hull shape design advantages. Start shape design from scratch on early stage of the project. Any information can be used for hull surface modeling. Short delivery time for preliminary model. Weight and center of buoyancy dynamic control. Always up-to-date lines.
Okay, that's enough. And then this one again, another example of body plan of offset table. And if you picture is too small, but in table is made of stations, number 1 and number 22. And station number is written here, right? Probably number 1 from the AP usually. 1, 2, 3. I cannot read this. Probably this one is low number here. Starting from front part this time. And then half breadths of each section. Say this is a number 4 section. Each waterline gives you half breadths of the section and gives you this offset table. So that's why you can, using this table, you can draw this curved surface, curves, lines, and body plan. All right. Okay. Any question? No question. Then we can move on to next present by Mr. Tien Han. Can you show your screen by sharing your screen?
Okay, I'll share my screen.